Hello, dear students. In last two lectures, we have discussed about the filtering of signals, mainly in the frequency domain. And in that, we have seen how we can design a digital filter using Butterworth approximation. So we have seen the implementation of low pass filter with some cutoff frequency. So today we will take one more example and we will design the filter, basically high pass filter, to remove low frequency noise. So for that, just check the question. Consider a segment of an ECG signal with low frequency noise, and ECG signal is sampled at 150 Hertz. So what is our objective? We have to design a first order digital Butterworth high pass filter for cutoff frequency of 30 Hertz, and for that we are assuming that order of the filter is 1, that is n equal to 1, and in that we have to use bilinear transformation, and capital T will be 1 by 150 second we are taking. Now let's start how to design this filter. We have already seen, like, if we want to design the digital filter, first thing is we have to design a analog filter. Now here it is, we have to design high pass filter. So it is always better if you design a low pass prototype filter and then convert that low pass filter into high pass using different frequency transformations. So the same procedure we will follow. Now what is given to us? So we are given with the cutoff frequency, that is 30 Hertz, and then we have given with sampling frequency, that is 150 Hertz. So how you can calculate the digital, or we can say frequency in digital domain? We know the formula, that is 2 pi fc by fs. So we are keeping the values 2 pi 30 Hertz by 150 Hertz, you will get 0.4 pi radians per second. So this will give us the frequency in digital domain, and it is given that we have to design a filter of order 1, that is n equal to 1, capital N equal to 1. Now as I mentioned that we have to design first a low pass filter, and we have to use bilinear transformation. So what is the frequency? First we will determine the frequency in analog domain, because we have to design an analog filter. So digital frequency we have obtained, or we can say frequency in digital domain we have obtained, that is 0.4 pi radians per second. And now we have to take that corresponding frequency in the analog domain, and for that, because it is mentioned that we have to use bilinear transformation, so we know the formula, that is 2 by t tangent frequency in digital domain, that is this omega c divided by 2, and we have to take that value omega c which is coming which has like value 0.4 pi. So we'll keep that value, and the value of capital T, it is 1 by 150. So we are taking that value, and if you keep this and solve, you will get the frequency in analog domain as 217.963 radians per second. Now first what we will do is we will design a low pass filter, prototype low pass filter, and then we will convert that into corresponding digital filter. So the system function, we know that system function of a normalized low pass filter. Focus on this, we are taking normalized low pass filter, that's why we kept 1 in the numerator. So it is given by, in general it is depending upon like order. If suppose order is capital N, so the equation will be 1 by s raised to power capital N plus bn minus 1. These are the filter coefficients, sn minus 1, similarly up to be 1s plus 1. Now, for our case, it is order is 1. That means capital N is 1. So if we keep the values of this capital N, you will get the equation as 1 by s plus 1. So this is the normalized, we can say, prototype low pass filter. Now, what is our motive? And we are, because we are designing a low pass prototype filter, so for this the cutoff frequency what we have assumed is 1, or we can say the pass band frequency what we have assumed is 1 radians per second. So now to design or to convert this into a high pass filter, we will use the frequency transformation. So we are given the different frequency transformation are there. Means if I want to convert a low pass filter at some frequency to new low pass filter at some other frequency, I can use again frequency transformation. Or if I want to convert a low pass filter into high pass filter, again I can use the frequency transformation, or low pass to band pass or band reject. So we have different formulas for frequency transformations. So what is our motive here? We have to design, or we have to convert that designed low pass prototype filter to high pass, and we know that we can change that S in a low pass filter by new S. And how will obtain that value? So we can, this formula, S is replaced by omega hp by S. Now here omega p is the low pass cutoff frequency in analog domain, so we are assuming that is 1 because we have designed the filter by keeping that value. This formula is basically by keeping that frequency as 1 radians per second. And then analog high pass cutoff frequency, which already we have calculated, and we represented it with omega c. And what was the value? It was 217.963 radians per second and divided by s. So this is a formula which we have to keep. Now this s we will replace in this normalized equation for low pass normalized filter. And if we keep these values, so you will get the filter, we can say analog high pass filter. So by keeping the value and substituting in that, so 1 by s plus 1, and we have to replace this s by 217.963 by s. So if I replace this 217.963 by s in this equation, you will get the analog equation for high pass filter. Now this is, we can say, analog high pass filter. So we have got the equation for analog high pass filter. Now, but our motive is we have to design a digital filter. So how we will obtain the digital filter now? For that, we know, because it is mentioned, there are different methods to convert analog to digital filter. We have bilinear transformation, we have impulse invariant, we have approximation of derivatives. So depending upon the question, because in question if you see it is mentioned that we have to use bilinear transformation with capital T as 1 by 150 second. So we'll keep the equation for bilinear transformation. And what is the equation for bilinear transformation? If I want to replace S in terms of Z, so you can see this equation, S is replaced by 2 by T whole in bracket is 1 minus Z inverse by 1 plus Z inverse. So this is standard equation for bilinear transformation. So here the variable what we want is, we want the value of capital T, and it is already given 1 by 150. So this S you will replace in the equation of this analog high pass filter. So if you keep this S as this 2 by 1 by 150, or we can say 2 into 150, that is 300, into 1 minus Z inverse by 1 plus Z inverse. Similarly, in denominator we have S, again we will keep these values, 300, 1 minus Z inverse by 1 plus Z inverse, plus you have to keep this value 217.963. So if you solve this little bit mathematically, you have to solve, and we will get the final equation as 0.5792 into 1 minus Z inverse divided by 1 minus 0.1583 Z inverse. So basically this equation is for digital high pass filter, which was the motive, and the cutoff frequency is this. For this is what we have chosen, what was given. We have to design with 30 hertz. So what are, just recall the steps. What we have done is, if we want to design a digital high pass filter, first step is you have to determine the frequency in analog domain. Then you will design a normalized prototype low pass filter considering the frequency as 1 radians per second. Then we will convert that particular filter into high pass depending upon whatever the cutoff frequency was given. In that, analog high pass filter is further changed to digital using the method mentioned, whether we have to use a bilinear transformation or any other method. So keeping that formulas in mind and applying that, you will get the final equation in terms of Z that corresponds to digital filter. So this is Hz, which represents the equation for or system function or transfer function for a digital high pass filter. So this was all in this lecture. Thank you.